As requested, this is a general review lecture for everything covered in the two play posits over valence bond theory. Recall that valence bond theory talks about how a covalent bond is formed by the pairing of two electrons with opposing spins, so spin up and spin down, in the region of overlap of atomic orbitals between two atoms. For example, we talked about how two hydrogen atoms with independent spins can come together and overlap to form a hydrogen-hydrogen single bond. We talked about how the hydrogen-hydrogen distance is a function of energy. So way out here, we have hydrogen atoms, and we're talking about the internuclear distance, or the distance between two separate atoms. So there's no bond out here. Then we saw, as we got closer and closer, that there was an ideal overlap. This ideal overlap is ideal because this is the point of lowest energy. So the more overlap we have between orbitals, the stronger the bond, but we can get too much of a good thing. Specifically, if the hydrogen-hydrogen nuclei get too close, we see this huge jump in the potential energy between them. And so we never stray past that bond length that we see in the hydrogen-hydrogen bond. We saw in our previous lecture that valence bond theory predicts the bonding for two atom and sometimes even three atom systems. But what if we get into a multi-atom system such as methane? We see that each hydrogen comes in with one electron. But if we examine the 2s and 2p orbitals, we see that there's only two spaces available where we can accept an electron into those 2p orbitals. So because of that, without doing something to tweak the valence bond theory a little bit, we would only see two bonds forming in a CH2 molecule, and we would also see that these bonds would have to be 90 degrees apart. When we talked about that for water, we said that the observed angles are 109.5 for a pure tetrahedron, and that's what we expect for CH4. But here, the valence bond theory model fails so spectacularly that we can't get more than two hydrogens attached to that carbon. So, how do we fix that? Valence bond theory invokes the hybridization or the hypothetical blending of atomic orbitals to describe the covalent bonding that's observed. It's very important to realize that the number of hybrid orbitals equals the total number of atomic orbitals combined. The electron pair geometry will be determined by the shapes and orientation of these hybrid orbitals, and they'll be different depending on how many atomic orbitals we combine. A key point to recall from earlier lectures is that when we're looking at the 2s and 2p orbitals, the 2s orbital is definitely lower in energy than these three 2p orbitals. Remember, when we have orbitals that are the same energy, we call these degenerate orbitals. What valence bond theory does is it takes these 2p orbitals and it mixes them with the 2s orbital in a process called hybridization. The result is that you get 4 hybrid orbitals, and these 4 hybrid orbitals are also going to be degenerate. So they're going to be equal in energy. So this is the unhybridized, and they mix to make the hybridized orbitals. There's a simple analogy to help you understand why these unhybridized orbitals that you put in have to equal the number of hybridized orbitals you get out. So I want you to think of this 2s orbital like 1 cup of red paint, and the 2p orbitals like 3 cups of blue paint. If you put in 4 cups of paint, your result is 4 cups, in this case, of purple paint, where the purple paint are going to be our hybrid orbitals. Again, I want to emphasize the fact that there is a difference in energy between the atomic orbitals, but once we hybridize these to make our sp3 orbitals, these are degenerate, so they are all the same energy. All right, so for methane, we know we've got this carbon in the middle, and each of these 1s orbitals represents a hydrogen atom. Because carbon has 4 electron domains, it needs 4 hybrid orbitals, which we get by combining 1s and 3p orbitals. So this is 4 hybrid orbitals. And in so doing, we see that each hydrogen is going to contribute 1 electron to those orbitals. And then, let's see if we switch to blue here, we can imagine the carbon also contributing 1 electron to each of those hybrid orbitals. If we think about ammonia, NH3, we've got that nitrogen in the middle, hydrogen, hydrogen, and hydrogen. And we know for the Lewis structure of ammonia that we've got hydrogen, lone pair of electrons, a hydrogen sticking out, and a hydrogen going into the plane. And so again, we have 4 electron groups. So we're going to need 4 hybrid orbitals. Those 4 hybrid orbitals are created by mixing 1s and 3p. Once we do that, we see that the lone pair of electrons occupies one of these sp3 orbitals, and hydrogen will have its electron, and then nitrogen will contribute its electron, and there is our tetrahedral electronic geometry and our trigonal pyramidal molecular geometry. All right, so what if we wanted to make the molecule BF3? Recall that boron comes in with an incomplete octet, and so it's only going to have 3 electron groups around the boron. So as a result of only having 3 electron groups, we only need 3 hybrid orbitals. We get those 3 hybrid orbitals by adding 2p orbitals plus the 1s orbital to get 3 hybrid orbitals. Now that does mean that we wind up with 2p orbital that is not hybridized. Okay, that's not important for this particular molecule, but it does retain that same amount of energy as the original 2p orbitals, and it does not participate in this hybridization down here. All right, so for boron trifluoride, we get the trigonal planar electronic and molecular geometry because we have these sp2 hybridized orbitals, and then the 2p orbitals come in from each fluorine and overlap with that sigma bonding. BeCl2, beryllium, is also going to come in with an incomplete octet. And so if we sketch the Lewis structure for BeCl2, we see that we only have 2 electron groups. So for bonding to occur, we only need 2 hybridized orbitals. So we take 1 p orbital, 1 s orbital, we combine them together to get our 2 hybrids, and then notice that these 2p orbitals that are not used in the hybridization retain their original energy, and they remain not hybridized. All right, so in the end, we see these sp hybrid orbitals on beryllium overlap with the p orbitals from chlorine, again in that head-on sigma fashion. Okay, so here's a question for you. Which of the following will have a central atom with sp3 hybrid orbitals? To figure this out, you really have to draw out the Lewis structure for every single one and figure it out from there. So let's do that. All right, now that I've got each of these Lewis structures drawn out, we know that an sp3 hybrid means that we've got something that's trying to fit 4 electron groups around that middle atom. So SF6, 6 groups, nope. BF3 with 3 groups, nope. H2CO with 3 groups, nope. Carbon dioxide with 2 groups, nope. That leaves us with PF3 with 4 electron groups, which would require that sp3 hybridization. All right, I already started talking about sigma bonds in this review lecture, but again, sigma bonds are going to be those covalent bonds formed from the end-to-end overlap of orbitals, kind of like 2 trains on a track where that track is going to be the x-axis. Pi bonds are the covalent bond formed from the side-to-side overlap of orbitals. These are mostly going to be from our p orbitals that are not hybrid orbitals. Okay, so that's a key point to look out for. We can also talk about single, double, and triple bonds. We know that all single bonds are going to be just sigma bonds. That's the basis of every bond we make. We have to have at least 1 sigma end-to-end overlap. A double bond will have that core sigma bond, but also a single pi bond. So we're looking out for that anytime we talk about having an sp2 hybridization. Triple bonds will consist of a sigma bond and 2 pi bonds. This is going to happen anytime we have sp hybridization. All right, so let's practice. How many sigma and pi bonds does CH2CH2 contain? All right, so our old pal ethene is back again. If we count first the sigma bonds, we have 1, 2, 3, 4, 5 sigma bonds. And then if we go back and count the pi bonds, we see that we only have 1 pi bond. If we dig deep into that ethene structure, we can ask what kind of hybrid orbitals are on the carbons of this molecule, because each carbon has 1, 2, 3 electron groups around it. This tells us that we have to have 1s plus 2p to give us 3 hybrid orbitals. On top of that sigma bond overlap in ethene, so we're still looking at ethene, we see that we also have these 2pz orbitals, and remember these are not hybrid orbitals. They got left out of that hybridization because we only needed sp2 on each carbon to make the sigma bond. All right, so as a result, this 2pz is going to have this overlap top and bottom, and that's going to make our pi bond. All right, so we can see this as a region of increased electron density both above and below the plane that contains the sigma bond. One other item worth noting: anytime we have just a single or sigma bond, this is going to allow free rotation around that axis. So we see that this whole thing on the end, this H2Cl can rotate. On the other end, we can see free rotation there as well. What is different is that as soon as we invoke this pi bond, because it has this electron density both above and below, it's going to lock the molecule. Okay, my iPad's overheating. Lock the molecule in place. All right, you get the gist. So that means that rotation is not permitted. All right, so how many sigma and pi bonds does the molecule CHCH contain? That's our old pal ethine. All right, so if we count these up, we have 1, 2, 3, 3 sigma bonds. And then each triple bond is made up of 1, 2 pi bonds. All right, so what about the hybridization on the carbon atoms? We see each carbon has 2 electron groups. And so because they have 2 electron groups, they only need 2 hybrid orbitals, which will be an s plus a p. So we would say this is sp hybridized. All right, so if we look at the bonding in ethine separately, we see that we have our sigma bond here between the 2 carbons, and then each hydrogen is here on the end. Next, we can look at the pi bonding, and that pi bonding is occurring between the 2 pz, both top and bottom, and it's also occurring on the 2 py. And so if we were to put all of this together, we would see that we've got these 4 areas of pi electron density. And then back in the middle there, we have this sigma bond. And this is the hot dog in a bun model, which will explain a triple bond every time. We have those 4 areas of pi density because we have overlap in 2 planes. And then last we have that sigma bond.